The observable universe is 93 billion light-years across. Yet, it may be only a microscopic fragment of everything that exists. Beyond its horizon may lie entire regions of reality whose light will never reach Earth. New James Webb observations reveal how massive space truly is and why humanity has never seen the complete cosmic map. Get ready. The journey begins now, 280 million years after the Big Bang. A galaxy was already shining brightly enough for its light to survive a journey of roughly 13.5 billion years. Only about 10 million years later, another galaxy already contained oxygen. Then, by the time the universe was around 700 million years old, a black hole with 50 million times the mass of the Sun had come to dominate most of the system surrounding it. These are not three scenes from a theoretical simulation. They are three objects detected in the real universe. Their names are MOM-GADES-GS-Z14-0 and QSO1. Each one represents a different cosmic clock, and all three clocks appear to be running faster than astronomers once expected. To understand how extreme this is, the entire 13.8 billion year history of the universe can be compressed into a single day. On that scale, the first of these galaxies would appear before the first half hour had passed. The enormous black hole would be present shortly after the first hour. The Sun would not form until late in the afternoon. Human civilization would arrive during the final fraction of the final second. The problem, then, is not simply that these objects are far away. The problem is how little time the universe had to build them. The first clock belongs to MOM-Z14. Astronomers see this galaxy as it existed only 280 million years after the Big Bang. Its cosmological redshift has been measured at 14.44, placing it among the earliest confirmed galaxies ever observed. At that stage, the universe was only about 2% of its current age. It should have been a place dominated by simple ingredients: hydrogen, helium, small fluctuations in density, vast regions of neutral gas. Yet MOM-Z14 was already bright. It was not alone, either. It belongs to a growing population of unexpectedly luminous early galaxies revealed by the James Webb Space Telescope. Before Webb began operating, theoretical studies predicted far fewer bright galaxies at such an early time. The first examples could have been statistical accidents. A rare object might appear in almost any survey. But the pattern continued. More bright galaxies appeared. More distances were confirmed. The exceptions began to look like a population. MOM-Z14 also carries unusual chemical information, including strong signs of nitrogen enrichment. That does not automatically prove any single explanation for its origin, but it shows that the early universe was already processing matter in ways that simple. Slowly developing pictures had not fully anticipated. The second clock is even more direct. JADES-GS-Z14-0 existed close to 290 million years after the Big Bang. Inside it, astronomers detected oxygen. That single element changes the story. The Big Bang produced almost all of its ordinary matter in the form of hydrogen and helium, along with tiny traces of a few light elements. It did not manufacture the oxygen found in planets, oceans, rocks, or living bodies. Oxygen had to be made later. It had to be forged inside stars. That required gas to collapse. Stars had to ignite. Nuclear fusion had to build heavier atomic nuclei. At least some massive stars then had to evolve far enough to release those elements into the surrounding gas. Only after that enrichment could oxygen become visible across an entire galaxy. All of those stages had already begun within the first 290 million years. Observations indicate that JADES-GS-Z14-0 contained roughly 5 to 20% of the Sun's metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. That is a remarkable level of chemical enrichment for such an early galaxy. Its heavy element abundance was estimated to be about 10 times higher than earlier expectations for that period. This does not mean the laws of stellar physics have failed. Massive stars can live very short lives. Some exhaust their fuel in only a few million years. The earliest stellar populations, therefore, had enough time to create oxygen. But the entire sequence had to begin early and proceed efficiently. The gas had to gather. Stars had to form in large numbers. Some had to die. Their products had to mix with the surrounding interstellar medium, and a new chemically enriched environment had to emerge, all while the universe was still in its infancy. Then comes the third clock. QSO-1 existed around 700 million years after the Big Bang. It is compact, measuring only about 1,300 light-years across, yet at its center lies a black hole with a mass of roughly 50 million suns. More startling still, that black hole accounts for at least 2/3 of the system's total mass. In nearby mature galaxies, the central supermassive black hole usually represents only a tiny fraction of the host galaxy's stellar mass. QSO-1 reverses that familiar relationship. The black hole is not a small central component inside a dominant galaxy. The black hole is the dominant object. Its surrounding system appears almost secondary. This conclusion did not come from brightness alone. Astronomers mapped the movement of hydrogen gas around QSO-1 and found a pattern of Keplerian rotation. The gas moved as if it were orbiting an enormous concentration of mass at the center. That allowed the central mass to be measured dynamically through gravity's effect on the surrounding material. The result was difficult to dismiss. A 50 million solar mass black hole was already present when the universe was only about 5% of its current age, and its environment contained very few heavy elements. Its metallicity was measured at less than half of 1% of the Sun's. That matters. A galaxy rich in generations of stars should contain more oxygen and other heavy elements produced through stellar evolution. QSO-1 instead appears chemically primitive. Even though its central black hole is already enormous, it presents a reversal of the traditional order. Astronomers once pictured galaxies forming first. Massive stars would then be born inside them. Some stars would collapse into black holes. Those black holes would feed, merge, and gradually grow into supermassive objects. QSO-1 suggests that, in at least some early systems, the black hole may have gained dominance before a substantial stellar galaxy had assembled around it. That does not yet reveal how the black hole formed. It does not confirm primordial black holes. It does not prove that every early galaxy followed the same path, but it forces the order of events to remain an open question. Which came first, the galaxy or the black hole together? These three clocks create a larger mystery. MOM-Z14 shows that bright galaxies were present after only 280 million years. JADES-GS-Z14-0 shows that stellar nucleosynthesis and chemical enrichment were already underway at nearly the same time. QSO-1 shows that a supermassive black hole could dominate a chemically primitive system by 700 million years. The early universe was not calm, it was not empty, and it was not developing at a uniformly slow pace. Gas was collapsing. Stars were igniting. Heavy elements were spreading. Black holes were gaining mass. Neutral hydrogen was beginning to lose electrons as energetic radiation transformed the space between galaxies. The first chapter of cosmic history may have been one of its most violent and productive. That leads to three questions. How early did the first stars truly form? Did galaxies build their central black holes? Or did some black holes help build the galaxies around them? And are the current models missing an important process? Or did the first measurements cause astronomers to overestimate what they were seeing? The answer may involve faster star formation. It may involve hidden black hole light being mistaken for starlight. It may involve rare environments that early surveys happened to find first. Most likely, different objects will require different explanations. Cosmology has not been broken. The evidence does not justify that claim. What has been broken is the comfortable assumption that the earliest galaxies must have been small, chemically simple, and slow to develop. The shock is not that known physics has stopped working. The shock is the time budget. The universe accomplished far more in its first few 100 million years than many models expected it to accomplish. But none of these three objects can be understood through beautiful images alone. The real evidence lies in the part of light that no human eye can see. The light from the first galaxies began its journey as ultraviolet radiation. By the time it approached Earth, the expansion of space had stretched that light into the infrared. That transformation is the key to everything the James Webb Space Telescope can see. MOM-Z14 did not send a photograph across the universe. Neither did JADES-GS-Z14-0 or QSO1. They released photons. Those photons crossed space for more than 13 billion years. Along the way, the universe changed. Galaxies formed, stars died, new elements appeared, entire clusters assembled, and space itself continued to expand. A photon is a packet of electromagnetic energy. It travels through empty space at the speed of light, but the wavelength it carries is not protected from cosmic expansion. As the universe grows, the distance between widely separated galaxies increases. The space through which ancient light is traveling stretches. The wavelength of that light stretches with it. Shorter wavelengths shift toward longer ones. Blue light moves toward red. Ultraviolet light moves beyond red and enters the infrared. Astronomers call this cosmological redshift. It is not simply an object changing color. It is a record of how much the universe expanded while the light was traveling. This is why the word redshift carries such importance. A high redshift does more than suggest that an object is far away. It places that object inside a specific period of cosmic history. A redshift of 14 does not mean the light looks 14 times redder to human vision. It means the observed wavelength has been stretched to roughly 15 times its original value. Radiation that left a galaxy in the ultraviolet can therefore arrive deep inside the infrared range. That is where Webb becomes essential. Cosmological redshift is sometimes confused with the Doppler effect. The two are related, but they are not identical. A Doppler shift occurs when a source moves through space relative to an observer. The familiar comparison is the changing pitch of a siren. The sound waves are compressed as the source approaches and stretched as it moves away. Light can behave in a similar way. A star moving toward Earth appears slightly blue-shifted. A star moving away appears redshifted. That effect is produced by motion through space. Cosmological redshift is produced mainly by the expansion of space itself. A very distant galaxy is not simply racing through a motionless cosmic arena. The arena is changing. The distance between large, gravitationally unbound structures grows because the geometry of the universe evolves. On smaller scales, gravity can overcome that expansion. The solar system is not being stretched apart. The Milky Way is not expanding internally. Galaxies and galaxy clusters can remain bound because their gravity is strong enough to hold them together. But across immense intergalactic distances, cosmic expansion dominates. Ancient photons carry the evidence. The earliest galaxies were filled with hot, massive stars. These stars released enormous amounts of ultraviolet radiation. That radiation helped ionize the hydrogen surrounding them and contributed to the transformation known as cosmic reionization. Yet almost none of that ancient ultraviolet light reaches Earth as ultraviolet. After more than 13 billion years of expansion, much of it arrives as near-infrared or mid-infrared radiation. Human eyes cannot see it. Hubble can detect a limited portion of the near-infrared range, but its design is centered largely on visible and ultraviolet wavelengths. Webb was built for the light that expansion had moved out of Hubble's most effective range. Its primary mirror measures 6.5 meters across. The mirror is not a single piece. It consists of 18 hexagonal segments made from beryllium, a material chosen because it is lightweight, strong, and stable at extremely low temperatures. Each segment carries a microscopically thin coating of gold. Gold reflects infrared light exceptionally well. Together, the segments form a collecting surface of more than 25 square meters. That large area allows Webb to gather photons from sources so faint that only a small number may reach the telescope during an observation. But collecting photons is only the beginning. Webb carries several instruments, and each performs a different part of the investigation. NIRCam, the near-infrared camera, operates across wavelengths from roughly 0.6 to 5 micrometers. It searches for faint sources. It reveals the shapes of galaxies. It compares their brightness through different filters. A galaxy may appear in longer wavelength filters while disappearing from shorter wavelength ones. That pattern can mark the position of the Lyman break and identify a possible high redshift object. NIRCam finds the suspect. NIR-SPECT conducts the interrogation. The near-infrared spectrograph separates incoming light by wavelength. Instead of recording a galaxy as a single point or smudge, it spreads the light into a spectrum. Inside that spectrum are emission lines, absorption features, chemical signatures, and information about motion. NIR-SPECT can observe many objects during the same exposure by using a microshutter array. Hundreds of thousands of tiny shutters can be opened or closed, allowing selected targets to send light into the spectrograph, while unwanted sources are blocked. This makes large surveys of faint galaxies possible. NIR-SPECT also contains an integral field unit, known as an IFU. The IFU does not produce only one spectrum for an entire object. It divides a small area of the sky into spatial elements and records a spectrum for each one. That creates a three-dimensional data cube. 2 dimensions describe position. The third describes wavelength. From that cube, astronomers can map where hydrogen, oxygen, or other elements are located. They can also measure how quickly gas is moving toward or away from the telescope in different parts of the object. That is, how QSO1's rotating gas could be traced. The picture showed where the object was. The IFU revealed what gravity was doing inside it. MIRI, the mid-infrared instrument, extends Webb's vision to wavelengths from about 5 to 28 micrometers. At those wavelengths, astronomers can detect cooler material, warm dust, and spectral features that cannot be reached by the near-infrared instruments. MIRI can separate light from stars, heated dust, and active galactic nuclei. It can also detect strong emission lines that shift into the mid-infrared from extremely distant galaxies. For these instruments to work, Webb must remain cold. Anything with a temperature emits infrared radiation. That includes the telescope itself. If Webb became too warm, its own thermal glow would overwhelm the faint infrared photons it was built to detect. The observatory would become like a camera trying to photograph a candle while the camera itself was on fire. Its location solves part of that problem. Webb operates near the second Sun-Earth Lagrange point, or L2, about 1.5 million kilometers from Earth. It does not sit motionless at a single point. It follows a large halo orbit around L2. From this region, the Sun, Earth, and Moon remain on roughly the same side of the observatory. That geometry allows one shield to block heat and light from all three. The shield has 5 layers. When deployed, it is roughly the size of a tennis court. Each thin layer reflects and disperses heat. Gaps between the layers allow thermal energy to escape sideways, rather than move directly toward the telescope. The sun-facing side remains warm, the mirror and scientific instruments remain in permanent shadow, operating at temperatures only a few dozen degrees above absolute zero. Mirae is cooled even further by a dedicated cryocooler. The result is an observatory sensitive enough to detect ancient infrared photons. Sometimes. However, even Webb needs help. That help can come from gravity. According to general relativity, mass curves space-time. When light from a distant galaxy passes near a massive foreground galaxy cluster, its path bends. The cluster acts as a gravitational lens. It can magnify a background object, stretch it into an arc, or create several images of the same source. This is not a perfect lens. The images can be distorted, and the amount of magnification must be modeled carefully. But the effect can reveal objects that would otherwise remain too faint to study. QS01 appeared 3 times because its light followed different curved paths around the foreground cluster. Hubble 2744. Glimpse 17,775 was brightened by another massive cluster. In both cases, nature provided an additional telescope made from gravity itself. Webb gathered the magnified light. Its instruments separated that light by wavelength. Only then could astronomers reconstruct the hidden object behind it. That is what Webb truly does. It does not simply take pictures of ancient galaxies. It receives light altered by expansion, filtered by gas, shifted into the infrared, and sometimes bent by gravity. Then it decodes the journey. But the ability to see farther is not enough to create a discovery. In the deep universe, a nearby galaxy wrapped in dust can disguise itself as a primordial galaxy at an enormous distance. Red can be the fingerprint of distance. It can also be the fingerprint of dust. And if those two possibilities are confused, an ordinary galaxy can become a false cosmic record. This is one of the greatest difficulties in studying the early universe. A distant object may appear as nothing more than a handful of pixels. Its structure is barely visible. Its light is faint. Much of the information astronomers want has been reduced to a few measurements taken through different filters. Yet from those few photons, they must determine distance, age, chemical composition, stellar mass, and sometimes even the presence of a growing black hole. The process begins with NIRCam. NIRCam does not observe the sky in only one broad infrared color. It uses multiple filters, each allowing a specific range of wavelengths to reach the detector. A galaxy may appear bright through one filter, faint through another, and completely absent through several shorter wavelength filters. That pattern matters. It allows astronomers to build a rough spectral energy distribution, often shortened to SED. A spectral energy distribution describes how much energy an object emits across different wavelengths. It is not yet a detailed spectrum. It is closer to a set of carefully placed sampling points. Each filter provides one point. Together, those points form the broad shape of the object's light. That shape may reveal whether the galaxy contains young blue stars, older red stars, hot dust, or an active galactic nucleus. It can also reveal a sudden drop in brightness known as a spectral break. For extremely distant galaxies, the most important of these is the Lyman break. Young, massive stars emit large amounts of ultraviolet light. Some of that radiation has wavelengths energetic enough to interact strongly with hydrogen. Inside a galaxy, neutral hydrogen absorbs part of it. More absorption occurs in the intergalactic medium, the thin gas spread through the enormous spaces between galaxies. The farther the light travels, the more clouds of hydrogen it encounters. Below a critical ultraviolet wavelength, very little light survives. This produces a sharp edge in the original spectrum. As cosmic expansion stretches the light, that edge moves into longer wavelengths. At a sufficiently high redshift, the break enters NIRCam's infrared filters. The galaxy then appears to drop out of the filters on the short wavelength side while remaining visible in the longer wavelength filters. Astronomers call this the dropout technique. A source missing from the bluer filters, but present in the redder ones, may be a galaxy from the cosmic dawn. But the word may is essential. The NIRCam measurements are used to calculate a photometric redshift. A photometric redshift is not one exact distance. It is a probability distribution. Computer models compare the observed filter pattern with templates representing different types of galaxies at different redshifts. The software then identifies which combinations provide the best match. One solution might place the object at an extreme redshift. Another might place it much closer, with large amounts of dust. Both can sometimes reproduce the same limited set of measurements. That creates a degeneracy. In astronomy, a degeneracy occurs when different physical situations produce similar observational signatures. A faint red source could be a young galaxy from the first few 100 million years. It could also be an older galaxy several billion years later. It could be a dust-obscured star-forming galaxy. It could be an active black hole hidden behind dense material. It might even be a cool star inside the Milky Way whose colors happen to resemble those of a distant galaxy. NIRCam can identify the suspect. It cannot always prove the identity. That requires spectroscopy. NIR-SPEC separates the incoming light into many narrow wavelength channels. Instead of a few broad points, astronomers receive a detailed pattern. That pattern contains emission lines and absorption lines. An emission line appears when atoms or ions release photons at specific wavelengths. Gas heated by young stars or by an active galactic nucleus can produce strong emission from hydrogen, oxygen, nitrogen, carbon, helium, neon, sulfur, and other elements. An absorption line forms when material removes photons from the light passing through it. Cooler gas in front of a bright source can absorb precise wavelengths associated with particular atomic transitions. Every element has its own set of transitions. In that sense, a spectrum behaves like a chemical barcode. But the barcode has been stretched. If several known lines appear at wavelengths longer than their laboratory values by the same proportion, astronomers can determine the redshift with far greater precision than broadband imaging allows. Sometimes individual lines are too faint to detect. In those cases, NIRSPEC may still confirm a source by resolving the shape and position of the Lyman break itself. A true break produced by hydrogen has a different profile from the smooth reddening created by dust. This distinction can turn a promising candidate into a spectroscopically confirmed galaxy. The spectrum also reveals the interstellar medium. The interstellar medium is the gas, dust, energetic particles, and magnetic fields occupying the space between stars inside a galaxy. It is the raw material for future stars. It is also the reservoir into which dying stars return newly created elements. Its chemical state records what has already happened inside the galaxy. Astronomers describe that chemical state using metallicity. In astronomy, every element heavier than hydrogen and helium is called a metal. Oxygen is a metal. Carbon is a metal. Nitrogen, silicon, sulfur, and iron are metals. Metallicity therefore measures the degree to which a galaxy's gas has been enriched by previous stellar activity. Another important quantity is the ionization parameter. This describes the intensity of ionizing radiation relative to the density of the surrounding gas. A high ionization parameter means atoms are exposed to a powerful field of energetic photons. The ratios between different emission lines can then reveal whether the energy comes mainly from hot young stars, shocks, or an active galactic nucleus. An active galactic nucleus, or AGN, forms when matter falls toward a supermassive black hole. The black hole itself emits no light from inside the event horizon. The surrounding accretion disk can be extraordinarily luminous. As gas spirals inward, it heats to extreme temperatures and releases radiation across the electromagnetic spectrum. In some young galaxies, an AGN can outshine all the stars combined. That creates one of the most dangerous traps in early galaxy studies. If astronomers assume that all the infrared light comes from stars, they may infer far too much stellar mass. A galaxy can then appear to have built tens of billions of stars impossibly early. When much of the light is actually being generated by gas around a black hole, little red dots demonstrated how serious this problem can be. Many initially appeared to be extraordinarily massive compact galaxies. Deeper spectra later revealed broad emission lines and other signs that accreting black holes were contributing heavily to their brightness. The galaxies did not disappear, but some of the most extreme stellar mass estimates became smaller. Dust creates another trap. Tiny grains of carbon-rich or silicon-rich material absorb ultraviolet and visible light. They re-radiate that energy at infrared wavelengths. A dusty galaxy can therefore become faint in short wavelength filters and bright in long wavelength filters, mimicking the colors of a high redshift dropout. Strong emission lines can cause a different kind of deception. If an intense line falls inside one broad NIRCam filter, it can increase the measured brightness of that entire filter. The result may look like a smooth stellar continuum or a spectral break when it is actually dominated by one narrow feature. Gravitational lensing adds another layer. A foreground cluster can magnify a background galaxy, making it appear far brighter than it would without the lens. That magnification is useful, but it must be modeled. An incorrect lens model produces an incorrect intrinsic luminosity. Since stellar mass and star formation rate are often inferred from luminosity, the error can spread into several other conclusions. Then there is cosmic variance. Webb's deepest surveys examine tiny patches of sky. Those fields may contain regions that are unusually dense or unusually empty. Finding several bright early galaxies in one field does not automatically reveal their average abundance across the entire universe. Larger surveys are needed before a local concentration can be treated as a universal population. For the most important discoveries, another observatory often joins the interrogation. ALMA studies light at millimeter and submillimeter wavelengths. It can detect fine structure lines produced by ionized carbon, oxygen, and other species in distant galaxies. These lines can provide extremely precise redshifts. They also probe cool gas, dust, and the conditions inside star-forming regions. Webb may identify a distant source and measure its ultraviolet or optical light. After redshift has moved that light into the infrared, ALMA can then test the same galaxy through a completely different portion of the electromagnetic spectrum. Agreement between independent instruments makes the case much stronger. This is why scientific language draws a hard line between a candidate and a confirmed object. A candidate has passed an initial selection. A confirmed galaxy has survived independent tests. The same caution applies to brightness. Brightness is an observation. Mass is an inference. A bright object may contain many stars. It may contain a feeding black hole. It may be magnified by gravity. It may have unusually strong emission lines. Or several of these effects may be operating at once. Only after those contributions are separated can brightness become a reliable estimate of physical mass. When MOM-Z14 survived that interrogation, it did more than retain its record-setting distance. Its spectrum also revealed how early the universe had begun changing its physical state. MOM-Z14 existed when the universe was only about 2% of its current age, yet its light suggests that the space around it had already begun to become transparent. That is almost as remarkable as the galaxy's distance. Using NIRSpec, astronomers confirmed MOM-Z14 at a cosmological redshift of 14.44. The light began its journey roughly 280 million years after the Big Bang and traveled through expanding space for about 13.5 billion years before reaching the James Webb Space Telescope. This was not simply another faint candidate selected from infrared colors. It survived spectroscopic examination. Its distance was written into the structure of its light. At first glance, MOM-Z14 appears unimpressive. It is a small while blurred source inside a field filled with closer galaxies. There are no visible spiral arms, no bright central bulge, no majestic structure like the Milky Way, but appearance is misleading. The galaxy is being observed at an age when the universe was still moving out of its cosmic dark ages. The first stars had only recently begun transforming the gas around them. And MOM-Z14 was already bright before Webb began science operations. Many theoretical studies predicted that galaxies this luminous would be extremely rare at such an early time. Small dark matter halos were expected to gather gas gradually. The gas would cool. Dense clouds would form. Stars would ignite in short episodes. Larger galaxies would then emerge through continued star formation and mergers. The process was expected to be fast by human standards, but still limited by gravity, cooling, feedback, and the amount of matter available inside early halos. Webb changed the observational side of that picture. MOM-Z14 belongs to a growing population of bright galaxies discovered in the first few 100 million years. According to the research team studying it, the observed abundance of such objects is roughly 2 orders of magnitude above some theoretical expectations developed before Webb's launch. That does not mean the standard cosmological model has been discarded. The underlying dark matter framework may still provide the correct, large-scale structure. The disagreement may instead lie in the complicated physics of ordinary matter. Gas may have cooled more efficiently. Star formation may have occurred in intense bursts. The first stellar populations may have produced more ultraviolet light per unit of mass. Feedback may have behaved differently in the dense conditions of the early universe. Some brightness may also come from sources that are difficult to separate, including highly ionized gas or growing black holes. The number of bright galaxies is the observation. The reason for their brightness remains under investigation. MOM-Z14 adds another layer to the mystery because of the environment through which its light escaped. About 380,000 years after the Big Bang, the universe experienced a transition known as recombination. Before that moment, space was filled with a hot plasma. Electrons moved freely among atomic nuclei. Photons repeatedly scattered from charged particles and could not travel far in a straight line. The universe was opaque. As expansion continued, the plasma cooled to around 3,000 Kelvin. Electrons could finally remain bound to protons, forming neutral hydrogen atoms. With fewer free electrons blocking their path, photons began traveling through space. The ancient light released during that transition is now observed as the cosmic microwave background. The universe had become transparent to that radiation, but it had not become transparent to every kind of light. Neutral hydrogen strongly absorbs ultraviolet photons, especially those energetic enough to interact with the electron inside a hydrogen atom. For tens or possibly hundreds of millions of years after recombination, the universe contained no large population of stars capable of producing new visible light. This interval is known as the cosmic dark ages. Matter was present. Dark matter was gathering into halos. Hydrogen and helium were falling into gravitational wells, but the sky contained no galaxies like those seen today. Eventually, the densest clouds collapsed far enough for the first stars to ignite. Those stars were likely massive, hot, and short-lived. Their surface temperatures allowed them to release intense ultraviolet radiation. Some of those photons carried more than 13.6 electron volts of energy, enough to remove the electron from a neutral hydrogen atom. That process is ionization. A neutral hydrogen atom exposed to an ionizing photon separates into a proton and a free electron around each early star-forming region. The surrounding neutral gas began changing state. Astronomers call a region of ionized hydrogen an H2 region. The name does not mean that 2 hydrogen atoms are present. It is spectroscopic notation. H1 refers to neutral hydrogen. H2 refers to hydrogen that has lost its electron. At first, these ionized regions were small. the intergalactic medium beyond them remained mostly neutral. Ultraviolet light could travel inside the bubbles, but it was absorbed when it reached the surrounding fog. As more stars formed, more ionizing photons escaped. The bubbles expanded. Galaxies formed groups, and neighboring bubbles began to overlap. Over hundreds of millions of years, the separate regions merged into an interconnected ionized universe. This transformation is known as the epoch of reionization. It did not occur everywhere at the same moment. Dense regions containing many galaxies ionized early. Emptier regions changed later. The process was uneven, patchy, and shaped by the distribution of the first luminous objects. By roughly 1 billion years after the Big Bang, most hydrogen in the intergalactic medium had become ionized. MOM-Z14 existed long before that process was complete. At 280 million years, the surrounding universe should still have contained large amounts of neutral hydrogen. That creates a problem for ultraviolet light trying to escape. Neutral hydrogen does not merely dim the signal. It can remove specific parts of the spectrum almost entirely. The farther a photon travels through neutral gas, the smaller its chance of surviving at the affected wavelengths. Yet MOM-Z14 spectrum shows signs that the galaxy was already clearing a region around itself. The exact size and structure of that region remain subjects of further observation, but the light indicates that MOM-Z14 was not sitting passively inside an untouched neutral fog. Its stars were affecting the intergalactic medium. They were releasing energetic radiation. Hydrogen near the galaxy was losing electrons. An ionized zone was beginning to form, giving some of the galaxy's radiation a path outward. This makes MOM-Z14 more than a timestamp. It is a source caught changing the physical state of the universe around it. The same photons that reveal the galaxy also record the resistance they encountered on the way out. Then there is nitrogen. MOM-Z14's spectrum shows unusual nitrogen enrichment, connecting it to a small group of other early galaxies with unexpectedly strong nitrogen signatures. Nitrogen acts like a chemical fossil. It preserves information about the stars that existed before the light left the galaxy. But reading that fossil is difficult. Nitrogen can be produced through more than one stellar pathway. In some stars, it forms when carbon and oxygen participate in nuclear reaction cycles that convert hydrogen into helium. The amount produced depends on the star's initial composition. At low metallicity, the situation becomes more complicated. Rotational mixing can carry newly created carbon and oxygen into regions where nitrogen production becomes more efficient. Stellar mass loss can then release that nitrogen into surrounding gas. Intermediate mass stars can also enrich galaxies with nitrogen during later stages of their evolution, but many of those stars require more time than the most massive stars before returning material to space. That time delay matters in a galaxy only 280 million years old. The observed nitrogen therefore depends on several connected factors: the initial mass distribution of the stars, their rotation rates, their ages, the metallicity of the gas from which they formed, the strength of stellar winds, the mixing of material inside the stars, and the speed at which enriched gas spread through the galaxy. Some proposed explanations involve unusual populations of massive stars. Others focus on dense star clusters, rapid chemical recycling, or conditions not commonly found in nearby galaxies. None has yet earned the right to become the final answer. MOM-Z14 confirms the enrichment. It does not, by itself, confirm the mechanism. That distinction protects the story from moving faster than the evidence. What the evidence does show is already powerful. A bright galaxy existed 280 million years after the Big Bang. It was producing enough energetic radiation to alter the hydrogen surrounding it. Its chemical spectrum contained nitrogen in proportions that challenge simple timelines of enrichment. and it belonged to a wider population of bright early galaxies that pre-Webb studies had substantially underestimated. MOM-Z14 was not merely present during the epoch of reionization, it was participating in it. Its stars were helping turn an opaque, neutral environment into the ionized universe through which later light could travel. Nitrogen raises a suspicion. Oxygen provides clearer evidence because every oxygen atom carries the history of a star that lived and died. The Big Bang did not produce any significant amount of oxygen. So, oxygen inside a galaxy, only 290 million years old, means that some stars had already completed their lives before that moment. They had formed, they had ignited, they had converted light elements into heavier ones, and they had released those elements back into space. The evidence comes from JADES-GS-Z14-0, a galaxy first identified and studied with the James Webb Space Telescope. When astronomers initially confirmed its extreme distance, JADES-GS-Z14-0 became one of the earliest known galaxies. Its light left when the universe was less than 300 million years old, roughly 2% of its current age. The galaxy was already unusual. It was bright in ultraviolet light. Its emission appeared extended, rather than concentrated into a single unresolved point, suggesting that much of its luminosity came from stars spread across the galaxy instead of one dominant active galactic nucleus. Webb also detected evidence of ionized oxygen through measurements involving its infrared instruments. But another observatory was needed to examine the galaxy through a completely different part of the electromagnetic spectrum. That observatory was ALMA. The Atacama Large Millimeter/Submillimeter Array is not a single telescope. It is a network of radio antennas operating together at high altitude in Chile's Atacama Desert. By combining signals from antennas separated across large distances, ALMA functions as an interferometer. It can achieve high spatial resolution while remaining sensitive to extremely faint radiation at millimeter and submillimeter wavelengths. Those wavelengths are ideal for studying cold gas, dust, and far infrared emission lines that have been stretched by cosmic expansion. In JADES-GS-Z14-0, ALMA detected the oxygen line known as O3 at a rest frame wavelength of 88 micrometers. Because the galaxy's light had been redshifted so dramatically, that 88 micrometer signal arrived at a wavelength of more than 1 millimeter. Webb and ALMA were therefore observing the same galaxy through different windows. Webb detected ancient ultraviolet and optical radiation shifted into the infrared. ALMA detected ancient, far infrared radiation shifted into the millimeter range. The two observatories were reading different parts of the same physical history. ALMA measured the galaxy's redshift at 14.1793. The uncertainty was only about 0.005%. That improved the precision of the earlier Webb redshift measurement by more than a factor of 180. This degree of precision matters. A small uncertainty in redshift affects more than the galaxy's position on a timeline. It changes estimates of luminosity, physical size, star formation rate, and the wavelength assigned to every spectral feature. With the ALMA measurement, astronomers could place JADES GS-Z14-0 far more accurately inside cosmic history. They could also be confident that the emission line was truly oxygen. The brackets around O3 carry a specific meaning. O3 refers to oxygen that has lost 2 electrons. Astronomers often call it doubly ionized oxygen. The brackets identify a transition described as forbidden. That word sounds more mysterious than it is. A forbidden transition is not physically impossible. It is simply very unlikely under the dense conditions normally produced in a laboratory. In low-density interstellar gas, however, an excited ion can remain undisturbed long enough to release a photon through that rare transition. Space provides the necessary conditions. The 88 micrometer O3 lines forms in ionized regions around hot, massive stars. These stars produce energetic ultraviolet photons capable of removing electrons from oxygen atoms. When the ions later move between closely spaced energy states, they emit far infrared photons at characteristic wavelengths. The line is also an important coolant. Gas inside an H2 region absorbs energy from radiation and collisions. Without a way to release that energy, the gas would continue heating. Oxygen ions help carry thermal energy away. A collision can excite an oxygen ion. The ion then emits a photon. That photon escapes, removing energy from the gas and allowing the region to cool. Cooling affects almost everything that happens next. It influences gas pressure. It changes how clouds fragment. It helps determine whether dense regions can collapse. And it affects how efficiently future stars can form. The O3 line is therefore more than a chemical fingerprint. It is part of the thermal machinery of a galaxy. Its brightness can provide information about the amount of ionized gas, the intensity of the radiation field, and the rate at which massive stars are forming. Combined with other lines, it can constrain electron density and ionization conditions. But the line cannot be translated directly into metallicity without additional information. Its strength also depends on temperature, density, geometry, and the spectrum of the ionizing source. For that reason, the research teams combined the ALMA observation with Webb measurements, including emission associated with oxygen and hydrogen at shorter rest frame wavelengths. Together, those data allowed the chemical abundance to be estimated more reliably. The result placed the metallicity of JADES-GS-Z14-0 at roughly 5 to 20% of the Sun's metallicity. That is low compared with the modern Milky Way. But for a galaxy only 290 million years after the Big Bang, it is unexpectedly high. The inferred abundance of heavy elements was about 10 times greater than some earlier expectations for galaxies at that age. The time available for creating those elements was severely limited. After the Big Bang, ordinary matter consisted almost entirely of hydrogen and helium. There were also tiny traces of lithium and a few other light nuclei. There was no large supply of carbon, no oxygen-rich gas, no silicon grains, no iron-bearing dust. The first metals had to be manufactured by stars. That process is known as stellar nucleosynthesis. A star begins by fusing hydrogen into helium. In sufficiently massive stars, the core later becomes hot enough for helium fusion. That stage produces carbon. Further nuclear burning can create oxygen and other heavier elements. The most massive stars continue through additional stages, building layered interiors containing neon, magnesium, silicon, sulfur, and eventually iron group nuclei. But the sequence does not continue forever. Fusion up to iron can release energy under the right conditions. Fusion beyond iron no longer supports the star in the same way. Once the core can no longer generate enough pressure to resist gravity, it collapses. The outer layers may then be expelled in a core collapse supernova. Some elements are also carried away before the explosion through powerful stellar winds. Either route can enrich the surrounding interstellar medium. Massive stars make this early enrichment possible because they live fast. The Sun is expected to remain on its main sequence for roughly 10 billion years. A star many times more massive than the Sun consumes its fuel at a vastly greater rate. The most massive examples can complete their evolution in only a few million years. That gives the early universe enough time for stellar death. But the schedule remains demanding. Before oxygen could appear throughout JADES-GS-Z14-0 gas had to collapse into the first stars. Those stars had to synthesize oxygen. At least some then had to expel it through winds or explosive death. The enriched material had to spread. It had to mix with more primitive hydrogen and helium, and new ionized regions had to illuminate that oxygen strongly enough for the O3 line to become detectable across 13.4 billion years. The detection does not require a long chain of slow, sun-like stars. It points toward rapid enrichment, driven largely by massive stellar populations. There is another clue. ALMA did not detect strong thermal emission from dust in JADI's GS Z14-0. That non-detection placed an upper limit on the dust-to-stellar mass ratio of approximately 0.002. In other words, the galaxy could already contain measurable oxygen while still possessing relatively little dust compared with its stellar mass. That distinction is important. Metals and dust are related, but they are not identical. Heavy elements enter the gas after stars expel them. Some later condense into solid grains. Those grains can grow inside dense interstellar clouds, but they can also be destroyed by supernova shocks and intense radiation. A young galaxy may therefore become chemically enriched before it develops a large, stable dust population. JADES-GS-Z14-0 and captures that transition. It is no longer chemically pristine, yet it is not a mature, dust-rich galaxy like many systems in the later universe. It occupies an early stage in which stars have already changed the chemical inventory. While the wider interstellar ecosystem is still developing, this finding does not prove that every galaxy in the cosmic dawn evolved at the same rate. JADES-GS-Z14-0 may occupy a rare, highly productive environment. Bright galaxies are easier to detect than faint ones, creating an observational bias toward the most active systems. The first objects found at extreme redshift may therefore represent the fastest growing members of a much broader population. Only larger samples can reveal what was typical. Still, the central fact remains: oxygen was present. The galaxy had experienced significant stellar processing, and chemical enrichment had begun earlier and proceeded faster than many pre-Webb expectations allowed. The first stars were racing against time, but at the centers of many early systems, another kind of object appears to have won the race before the galaxy itself. A black hole can swallow light, but when it swallows matter, it can generate enough radiation to push its own food away. That contradiction lies at the heart of the early black hole problem. A black hole itself is dark. Once matter crosses the event horizon, no signal from inside can return to the outside universe. But most matter does not fall directly through that horizon. It arrives carrying angular momentum. A gas cloud may be moving around the center of a galaxy. A star may approach the black hole along a curved orbit. Two streams of gas may collide without canceling all their sideways motion. Gravity pulls the material inward. Angular momentum keeps it circling. The result is an accretion disk. An accretion disk is a flattened, rotating structure of gas, plasma, and sometimes disrupted stellar material. The inner regions orbit faster than the outer regions. That difference in speed creates shear. Neighboring layers pull against one another. Magnetic fields become stretched, twisted, and amplified. Turbulence develops through processes that include the magneto-rotational instability. This magnetic turbulence performs a critical job. It transports angular momentum outward. Some gas gains angular momentum and moves to a wider orbit. Other gas loses angular momentum and spirals inward. Without that transfer, material would remain in orbit instead of reaching the black hole. As gas moves closer, gravitational energy is converted into heat. The inner disk can reach temperatures of hundreds of thousands or millions of degrees. It releases ultraviolet radiation, X-rays, and other high-energy photons. A feeding black hole can therefore become one of the brightest objects in the universe. The light does not come from inside the black hole. It comes from matter during its final journey toward the event horizon. This process is extremely efficient. Ordinary nuclear fusion inside stars converts less than 1% of the original mass involved into released energy over the full reaction chain. Accretion around a black hole can convert a much larger fraction of infalling mass into radiation. The exact efficiency depends on the black hole's spin and on how close the inner edge of the disk can approach the event horizon. A rapidly spinning black hole can extract far more radiative energy from the same amount of gas than a slowly spinning one. But high efficiency creates a problem. More radiation means greater outward pressure. As photons move through the surrounding material, they interact with electrons. Each interaction transfers momentum. The accumulated pressure can oppose the inward pull of gravity. At low accretion rates, gravity wins easily. Gas continues falling. The black hole gains mass. As the inflow increases, however, the accretion disk becomes brighter. The outward radiation pressure grows stronger. Eventually, the system approaches a balance. Gravity pulls matter inward. Radiation pushes it outward. This balance is known as the Eddington limit. The Eddington limit is not a wall surrounding the black hole. It is not a universal number shared by all black holes. It scales with mass. A larger black hole produces stronger gravity and can sustain a greater luminosity before radiation pressure becomes powerful enough to resist the inflow. The limit is also based on assumptions. It usually describes a roughly steady symmetric flow of ionized gas. Real accretion can be clumpy, directional, magnetized, and unstable. Under certain conditions, matter can enter through dense channels while radiation escapes through lower density regions. A black hole can then exceed the classical Eddington rate for a period of time. Super Eddington accretion is physically possible, but sustaining it is difficult. The same energy that allows the black hole to shine can heat the surrounding gas, launch winds, and reduce the fuel supply. The faster the feeding becomes, the more violently the system can react against it. For astronomers, the Eddington limit provides a useful reference point. It shows how quickly a black hole can grow under idealized, continuously fed conditions. The associated growth interval is often called the Salpeter time. For a commonly assumed radiative efficiency of around 10% and accretion near the Eddington limit, the black hole's mass increases by a factor of about 2.7 every 45 million years. 45 million years sounds short beside the age of the universe, but exponential growth needs many such intervals. A black hole born from the collapse of a massive star might begin with roughly tens or hundreds of solar masses. To grow from 100 solar masses to 1 billion requires an increase by a factor of 10 million. That demands a little more than 16 Salpeter intervals. Under near-perfect conditions, the process takes more than 700 million years. The calculation assumes continuous feeding, no long interruptions, no shortage of cold gas, no powerful outflow cutting off the supply, no time lost while the black hole moves through a low-density environment, no major change in radiative efficiency, no failure to remain near the Eddington rate. The early universe did not guarantee any of those conditions. Gas was abundant, but abundance alone was not enough. It had to lose energy and angular momentum before reaching the central region. Star formation competed for the same material. Supernovae heated and expelled gas. Radiation from young stars altered the surrounding medium. The black hole's own activity added another layer of feedback. As the accretion disk brightened, radiation heated nearby gas. Disk winds could carry matter outward at thousands of kilometers per second. Jets could transport energy far beyond the central region. A black hole might create the very conditions that ended its meal. Fuel delivery could also be intermittent. Galaxy mergers can drive gas toward the center, but mergers do not provide a smooth, permanent flow. Gravitational interactions disturb the gas. Some moves inward, some forms stars, some is thrown into extended tidal structures. Each episode takes time. Black hole mergers face their own delays. Two galaxies can merge while their central black holes remain far apart. Dynamical friction must first slow the black holes and bring them closer. After forming a bound pair, they must continue losing orbital energy, stars, gas, and eventually gravitational waves may carry that energy away. Only then can the two black holes unite. The final merger can produce a gravitational wave recoil. If the waves carry momentum unevenly, the new black hole receives a kick. In a small early galaxy with weak gravity, that kick may displace the black hole from the densest gas or even eject it completely. A displaced black hole loses access to the best fuel. Growth slows again. The problem becomes especially severe for quasars observed less than 1 billion years after the Big Bang. Some contain black holes, hundreds of millions or billions of times the mass of the Sun. If they began as ordinary stellar remnants, they needed to form very early and feed almost without interruption. A later birth leaves too few salpeter intervals. A low-duty cycle leaves too many empty intervals. A high radiative efficiency means more incoming mass is converted into energy instead of remaining in the black hole, slowing mass growth even further. There are ways to reduce the pressure on the timeline. A black hole may begin with a larger seed. It may experience periods of super-Eddington accretion. Dense galactic environments may deliver gas more effectively than simple models assume. Several growth channels may operate in the same object, but the observations must determine which processes actually occurred. A possible mechanism is not evidence that the mechanism operated in every early galaxy. That is why the early black hole mystery is best described as a growth problem. It is not proof that gravity failed. It is not proof that radiation stopped exerting pressure. It does not show that the Eddington limit disappeared. Instead, the observations reveal that the universe found ways to assemble large black holes within a very restricted time budget. The task is to identify those pathways without treating the most dramatic explanation as the default answer. Then Webb discovered a population that made the growth problem feel urgent. The objects were small. They were red. They were remarkably bright. And after a brief period of cosmic history, they almost disappeared. If all the light from the little red dots came from stars, some early galaxies would have needed to build far too much stellar mass in far too little time, but that assumption was wrong. The objects first appeared in Webb observations as compact red sources. They were small on the sky. Many were unresolved or only slightly extended. Their light rose strongly toward longer infrared wavelengths. Astronomers gave them an informal but memorable name: little red dots. At first, their brightness created an alarming interpretation. If the infrared light came from stars, the stars had to be numerous. Some estimates gave the objects stellar masses comparable to much larger modern galaxies. Yet many little red dots existed during the first 1.5 billion years after the Big Bang. There seemed to be too little time to create that many stars. The problem reached beyond individual galaxies. In the standard cosmological framework, ordinary matter falls into halos dominated by cold, dark matter. The number of massive halos available at an early time is limited. If too many galaxies had already converted a large fraction of their gas into stars, the inferred stellar masses could approach or exceed the amount of ordinary matter their halos were expected to contain. That was the origin of the most dramatic claims. The galaxies were called impossible. Some were described as universe breakers. But the calculation depended on one critical assumption. It treated most of the observed light as starlight. Webb's later spectroscopy began separating that light into its physical components. The result changed the story. Little red dots are not distributed evenly through cosmic history. They begin appearing in large numbers around 600 million years after the Big Bang. Their population remains prominent through an early period of galaxy growth, then declines rapidly around 1.5 billion years after the Big Bang. Comparable objects are rare in the nearby universe. That rise and disappearance suggest that the red dot phase is connected to a particular stage of early galactic development. The strongest clue came from emission lines. Atoms and ions in hot gas emit light at specific wavelengths. If the gas is nearly stationary relative to the center of a galaxy, the resulting line remains narrow. But gas near a massive black hole can move extremely fast. One side of an orbiting region approaches the observer. Its light shifts slightly toward shorter wavelengths. The opposite side moves away. Its light shifts toward longer wavelengths. gas also moves along many tilted and irregular paths. All those shifts overlap. Instead of one narrow spectral line, the telescope records a broad feature. This is Doppler broadening. In a sample of little red dots with suitable spectroscopic observations, about 70% showed evidence of gas moving at roughly 1,000 kilometers per second. That is close to 2 million miles per hour. Such speeds do not automatically prove the presence of a black hole. Explosions, outflows, and galaxy-scale turbulence can also accelerate gas, but persistent broad emission lines centered on a compact source are a well-established signature of an active galactic nucleus. The gas appears to be moving deep inside a powerful gravitational potential. A dense star cluster can create strong gravity, but the extreme compactness and luminosity of many little red dots favor accreting supermassive black holes. The central engine changes the interpretation of the entire object. An active galactic nucleus, or AGN, can emit enormous amounts of energy from a region smaller than the surrounding galaxy. Gas spiraling through the accretion disk heats up. The inner disk releases ultraviolet and extreme ultraviolet radiation. Hot plasma close to the black hole can generate X-rays. That radiation then interacts with material farther out. Gas absorbs the energetic photons. Electrons are removed from atoms. The ionized gas later emits new photons at characteristic wavelengths. Dust absorbs ultraviolet and visible radiation, heats up, and re-radiates the energy in the infrared. The original blue or ultraviolet light can therefore emerge as a much redder spectrum. This process is known as reprocessing. The observed redness does not have to mean that the object contains an enormous population of old red stars. It may mean that a young, powerful central source is hidden inside dense material. That difference is crucial. Astronomers estimate stellar mass by comparing an object's spectral energy distribution with models of stellar populations. The models include stars of different masses, ages, and metallicities. They predict how much light a given population should produce at each wavelength. If an AGN contributes strongly but is omitted from the model, the fitting process assigns its light to stars. The inferred stellar mass rises. The age estimate can also become distorted. A red spectral shape may be interpreted as a population of older stars with high mass-to-light ratios. A sudden change in brightness between filters may resemble a Balmer break, a feature associated with stellar atmospheres and the age of a population. But strong emission lines, dense gas, and reprocessed AGN light can produce similar broadband colors. Different physical systems can again occupy the same observational disguise. This is why some early mass estimates became so large. The models were being asked to explain black hole light using stars alone. Once AGN components were included, the required stellar populations became smaller. Fewer stars meant lower stellar masses. Lower stellar masses fit more comfortably within the ordinary matter available in early dark matter halos. The apparent crisis weakened. The galaxies remained unusual. Their black holes remained difficult to explain. But the claim that they contained impossibly massive stellar populations no longer applied to many of them. This correction demonstrates how an observational crisis can arise. First, a new instrument enters unexplored territory. It detects objects unlike those in the nearby universe. Existing templates are applied because no better templates yet exist. The resulting masses appear to conflict with theory. Then improved spectra revealed that the templates were incomplete. The data were real. The first interpretation was not, "That does not mean every little red dot has now been solved." The name describes an observational appearance, not one proven physical class. Some may be dominated by active black holes. Some may contain dense star-forming regions. Some may combine a growing black hole with a compact stellar population. Different amounts of dust, gas, and scattered light can produce similar red colors, even among objects containing AGN. The geometry may vary. One black hole may be viewed through a thick equatorial layer of gas. Another may be enclosed inside a more spherical cocoon. A third may have openings through which radiation escapes in preferred directions. Orientation changes what the telescope sees. The little red dots are also surprisingly weak in X-rays, compared with many active galaxies at lower redshift. That observation remains important. It could mean the central engines differ from familiar quasars. It could mean dense gas absorbs or traps much of the X-ray radiation. It could also indicate that some red dots are not dominated by black holes at all. The data do not yet justify a single answer for the whole population. Their disappearance after about 1.5 billion years creates another unresolved question. The objects may physically transform. Their gas cocoons may thin. Their host galaxies may grow larger and less compact. Their central black holes may become visible as more familiar blue quasars, or the conditions that produced the red dot appearance may simply become less common as the universe expands and galaxies evolve. Those possibilities remain under investigation. What spectroscopy has established is narrower, but solid. Many little red dots contain rapidly moving gas. A large fraction show evidence of active, accreting black holes. Their luminosity cannot safely be assigned entirely to stars. And some of the most extreme early stellar mass estimates were inflated because black hole light had been misidentified. A candidate mass derived from brightness is not the same as a direct mass measurement. A red color is not a physical identity. A compact source is not automatically a mature galaxy. The lesson is not that theoretical models can never be challenged. The lesson is that the observation and the interpretation must be separated before any crisis is declared. For many little red dots, identifying AGN light removed part of the conflict, but it also shifted the mystery. If the objects did not contain impossibly large stellar populations, they contained growing black holes bright enough to imitate them. The universe-breaking galaxy problem became an early black hole problem. Separating black hole light from starlight resolved part of the crisis. But QS01 revealed at least one case even more extreme than the original estimates. QS01 is only about 1,300 light-years across. At its center lies a black hole with roughly 50 million times the mass of the Sun. That black hole accounts for at least 2/3 of the mass of the entire system. The proportions are difficult to reconcile with familiar galaxies. The Milky Way stretches about 100,000 light-years across and contains hundreds of billions of stars. Its central black hole, Sagittarius A star, has a mass of roughly 4 million suns. That sounds enormous. Yet compared with the stellar mass of the Milky Way, Sagittarius A star contributes only a tiny fraction. QS01 is different. Its black hole is more than 10 times as massive as Sagittarius A star. Its surrounding system is far smaller, and it existed when the universe was only around 700 million years old. The central black hole does not appear to be a minor component of an already mature galaxy. It appears to dominate almost everything around it. QS01 is classified as a little red dot. Its full designation connects it to the foreground galaxy cluster Abell 2744, also known as Pandora's cluster. Abell 2744 lies much closer to Earth than QS01. It contains a vast concentration of galaxies, hot gas, dark matter, and intercluster material. Together, that mass curves the surrounding spacetime. Light from QS01 traveled toward the cluster from far behind it. Instead of following one straight path, the light was bent around the warped region. This is strong gravitational lensing. Weak gravitational lensing produces subtle distortions in the shapes of background galaxies. Strong lensing is more dramatic. It can stretch galaxies into arcs, magnify their light, and create multiple images of the same source. QS01 appears in 3 separate positions around Abell 2744. Those are not 3 similar objects. They are 3 images of the same ancient system. The light followed different routes through curved spacetime before reaching Webb. The geometry acts like a natural telescope. It does not create new photons. It redirects and concentrates light that would otherwise be spread across a fainter image. That magnification allowed astronomers to examine QSO-1 in far greater detail than its intrinsic brightness would normally permit. But gravitational lensing must be treated carefully. A cluster is not a simple glass lens. Its mass is distributed unevenly among galaxies, hot gas, and dark matter. Astronomers must reconstruct that distribution to estimate how much a background source has been magnified. An incorrect lens model can produce an incorrect luminosity, size, or mass. QSO-1 offered an important advantage. Its 3 images provided multiple views of the same source through the same foreground gravitational structure. Their positions, shapes, and brightnesses helped constrain the lensing geometry. After correcting for magnification, the system remained extraordinarily compact. Earlier observations had already suggested a central black hole of around 40 million solar masses. But those estimates were indirect. Most black hole masses in the distant universe are inferred from the brightness of an active nucleus and the width of its emission lines. The method is called a virial estimate. Gas close to a black hole moves rapidly. The black hole's gravitational pull determines the gas velocity. The broadline region's size can then be estimated through luminosity relations, calibrated using active galaxies in the nearby universe. Those relations are useful, but they depend on assumptions. They assume that early black holes behave like later ones. They assume a particular geometry for the gas. They assume the observed velocity is dominated by gravity rather than winds, shocks, or radiation pressure. At a distance corresponding to the first billion years, those assumptions had never been tested with a direct dynamical measurement. QSO-1 made that test possible. Astronomers used the integral field unit inside Webb's near-infrared spectrograph. The NIR-SPEC-IFU separated a small region around QSO-1 into spatial elements. For each element, it recorded a spectrum. Hydrogen emission lines revealed the velocity of the gas. Gas moving toward Webb produced a slight blue shift. Gas moving away produced a slight red shift. By mapping those shifts across QSO-1, the researchers reconstructed how the gas moved around the center. The pattern was not random. One side showed motion toward the telescope. The other showed motion away. The gas was rotating. More importantly, its speed changed with distance from the center in the way expected for Keplerian motion. Keplerian rotation occurs when orbiting material is controlled mainly by a concentrated central mass. The solar system provides the familiar example. Mercury moves around the Sun faster than Earth. Earth moves faster than Neptune. Orbital speed decreases with increasing distance because most of the system's mass is concentrated in the Sun. A galaxy dominated by a widely distributed population of stars behaves differently. If large amounts of mass are spread throughout the system, gas at increasing distances continues to feel the gravity of additional enclosed matter. The velocity pattern no longer follows the clean signature of a single dominant central object. QSO-1's gas behaved as though most of the mass were concentrated at the center. This allowed the black hole to be weighed through its gravitational influence. The result was approximately 50 million solar masses. This was the first direct dynamical measurement of a black hole's mass within the first billion years of cosmic history. It also supported the earlier indirect estimates. At least in this case, the methods calibrated using closer active galaxies had not exaggerated the black hole's mass. The measurement became even more striking when the mass of the surrounding system was considered. The black hole accounts for at least 2/3 of QSO-1's total mass. The word total requires care. Astronomers are measuring the matter that can be constrained within the compact observed system. Unseen material and uncertainties in geometry remain relevant, but no reasonable correction turns QSO-1 into a normal modern galaxy. Its central black hole outweighs the visible stellar component by an extraordinary margin. The chemical evidence points in the same direction. INI-RSpec's spatially resolved measurements showed that the gas consists almost entirely of hydrogen and helium. The metallicity is less than half of 1% of the Sun's. That makes QSO-1 one of the most chemically pristine galactic environments ever measured. A system rich in generations of stars should contain more oxygen, carbon, nitrogen, silicon, and iron. Massive stars manufacture many of those elements. Supernovae and stellar winds then spread them into the surrounding gas. QSO-1 does not show the chemical record expected from a large, mature stellar population. The black hole is enormous. The galaxy around it is small. The gas remains primitive. Together, those facts create a specific problem. The traditional sequence begins with a galaxy. Gas falls into a dark matter halo. Stars form. Some massive stars collapse into black holes. The black holes feed and merge. Over time, one central object grows into a supermassive black hole, QSO. One does not fit comfortably into that order. Its black hole appears too dominant relative to the surrounding stellar system. That does not prove the black hole literally existed before all stars. It does not reveal the mass or nature of the original seed. And it does not establish one formation pathway for all early supermassive black holes. Several proposed origins remain possible. A massive gas cloud could have produced a large initial seed. Dense stellar environments could have accelerated mergers. An early black hole could have experienced periods of rapid accretion. More exotic possibilities have also been discussed. But QSO-1 does not choose between them. The observation confirms the final state visible 700 million years after the Big Bang. A 50 million solar mass black hole, a compact surrounding system, a mass fraction dominated by the black hole, and gas with less than 0.5% of the Sun's metallicity. The formation history must be reconstructed from that evidence. The proper conclusion is not that a primordial black hole has been confirmed, nor is it that direct collapse has been proven. The proper conclusion is narrower and stronger. At least one supermassive black hole gained gravitational dominance before its host developed the mass and chemical maturity of a familiar galaxy. QSO-1 allowed astronomers to weigh the black hole, but another little red dot revealed what may be hiding such black holes from the rest of the universe. In the deepest spectrum ever obtained from a little red dot, astronomers found more than 40 emission and absorption features. 16 of them came from iron. Together, they formed a spectral forest unlike anything previously seen with such clarity in this population. The object is called GLIMPS 17,775. It lies behind the massive galaxy cluster Hubble S1063. As with QSO-1, the foreground cluster bends and magnifies light from the much more distant source. The alignment gave Webb access to a level of detail that would otherwise have required far more observing time. Webb collected light from GLIMPS 17,775 for about 30 hours. After accounting for gravitational magnification, the resulting signal was comparable to what an unlensed observation might have required roughly 80 hours to achieve. That is an exceptionally deep exposure for one tiny red source. The observation was not originally designed only to solve the little red dot mystery. The wider program searched for faint early galaxies and possible signatures of the first stellar populations. GLIMPS 17,775 happened to fall in the right place. The combination of a sensitive infrared telescope, a massive gravitational lens, and a long exposure created an unusually detailed spectrum. A normal image would show little more than a red point. The spectrum revealed an entire physical environment. Hydrogen was present. Helium was present. Oxygen and sulfur appeared. Iron produced at least 16 separate features. Some lines were emitted strongly. Others appeared in absorption. Several were unusually broad. The challenge was to find one physical structure capable of producing all those signatures at the same time. A simple rotating cloud did not work. If the broad lines came entirely from orbital motion, the gas would need a particular distribution of velocities and geometry, but that explanation failed to reproduce the shapes of several features. The lines did not merely show ordinary Doppler broadening. Another process was affecting the photons. That process was electron scattering inside a hot, dense, partially ionized gas. Large numbers of free electrons move at high thermal speeds. A photon trying to escape can collide with those electrons. The photon is not destroyed. Its direction changes. Its energy may shift slightly because the electron itself is moving. One interaction produces a small effect. Many interactions produce a broad distribution of wavelength changes. A photon originally emitted at one narrow wavelength can emerge as part of a much wider line. This creates broad wings around spectral features. The line may look as though all the emitting gas is moving at extreme bulk velocity, even when part of the width actually comes from repeated scattering. The distinction matters. Doppler broadening caused by orbital motion can be used to estimate gravitational mass. Broadening caused by electron scattering reveals the density, temperature, and optical depth of the surrounding material. Optical depth describes how difficult it is for radiation to escape. A medium with low optical depth is transparent. Most photons pass through without interacting. A medium with high optical depth is opaque. Photons are absorbed or scattered many times before escaping. Glimpse. 17,775 appears to contain gas with substantial optical depth. The central source is not shining directly into open space. Its radiation is being processed inside a cocoon. The cocoon absorbs energetic photons. It ionizes atoms. It scatters light through free electrons. It produces new emission lines. Then it releases part of the energy at different wavelengths. The observed spectrum is not a direct view of the central engine. It is the central engine after the surrounding gas has rewritten its light. Hydrogen provides one of the clearest examples. The broad hydrogen feature could not be explained well by a simple model of rotating gas. Electron scattering produced a better match to its shape. Helium added independent evidence. Some helium features appeared through fluorescence. Fluorescence begins when an atom or ion absorbs a high-energy photon and moves into an excited state. It then releases energy through one or more lower-energy photons at characteristic wavelengths. The process requires both a powerful radiation source and suitable surrounding material. Helium absorption also showed that dense gas lay in front of the source along the line of sight. Oxygen and sulfur constrained the ionization conditions. Their electrons require specific energies to remove or excite. The relative strengths of their spectral lines therefore reveal how intense and energetic the radiation field must be. Then came the iron forest. Iron has a complicated electron structure. It can produce many transitions at closely spaced wavelengths. Under the right conditions, high-energy radiation excites the ions and generates numerous emission features. In glimpse, 17,775 16 iron lines appeared together. They could not be produced easily by an ordinary young stellar population. The lines required a strong source of energetic photons interacting with dense gas. Iron fluorescence pointed toward an active accretion process. The combined evidence created a coherent picture. At the center lies a rapidly growing black hole. Around it is a thick envelope of hot, dense, partially ionized gas. The black hole's accretion flow generates intense radiation. The cocoon traps and reprocesses much of that energy. Electron scattering broadens the lines. Fluorescence produces the iron and helium features. Absorption reveals material between the central source and the observer. Emission from oxygen, hydrogen, helium, sulfur, and iron maps the physical state of the envelope. This interpretation is known as the black hole star scenario, often shortened to BH star or BH asterisk. The name is misleading if taken literally. A black hole star is not a normal star undergoing nuclear fusion in a stellar core. It is a theoretical configuration in which a rapidly accreting black hole is enclosed inside a dense, gaseous envelope. The outer gas can behave like an artificial photosphere. Radiation generated near the black hole struggles to escape directly. It is scattered, absorbed, and re-emitted until the surrounding structure produces a star-like spectral appearance. From far away, the object may look compact, bright, and red. Inside, the power source is not ordinary stellar fusion. It is accretion. The glimpse, 17,775 spectrum, provides the strongest evidence yet for this model in a little red dot. But strongest evidence is not the same as final confirmation. The result concerns one object. Other little red dots may contain different mixtures of stars, gas, dust, and active black holes. Even within glimpse, 17,775 models depend on assumptions about geometry, density, temperature, chemical abundance, and the shape of the hidden radiation field. Future observations must test whether the same model predicts additional spectral features correctly. Still, the convergence of more than 40 lines is difficult to dismiss. Hydrogen, helium, oxygen, sulfur, and iron all point toward a dense environment surrounding a powerful source. The breadth of the lines supports electron scattering. The iron forest requires high-energy excitation. The absorption features place gas directly in the path of escaping radiation. No single line carries the conclusion. The strength comes from many independent pieces agreeing. This may also help explain why many little red dots appear weak in X-rays. A dense cocoon can absorb high-energy photons before they escape. The energy is then redistributed into ultraviolet, optical, and infrared wavelengths. The black hole may be growing vigorously while remaining hidden from surveys that expect an unobscured X-ray source. The object would not be inactive. It would be buried. That changes how early black hole populations are counted. If many growing black holes were surrounded by optically thick gas, traditional X-ray surveys could have missed them. Webb's infrared sensitivity would then reveal a phase of black hole growth that had been largely invisible. The red color would no longer be a cosmetic detail. It would be evidence of the physical structure hiding the central engine. These gas cocoons may conceal the light of black holes, but they cannot conceal the effect those black holes have on the galaxies forming around them. A black hole does not simply consume matter. It can determine whether billions of solar masses of surrounding gas become stars or are driven out of the galaxy entirely. This influence is known as active galactic nucleus feedback. The name sounds technical. The basic idea is simple. Matter falls toward a supermassive black hole. Before crossing the event horizon, it releases enormous amounts of energy. That energy interacts with the surrounding galaxy. The black hole is tiny compared with its host. Its event horizon may be smaller than the solar system, while the galaxy extends across thousands of light years. Yet the energy generated close to the black hole can travel far beyond the central region. It can heat gas, compress clouds, launch winds, and alter the rate at which new stars form. That creates one of the strangest relationships in astrophysics. A black hole may contain only a small fraction of a mature galaxy's total mass, but it can influence the future of almost everything inside that galaxy. The process begins in the accretion disk. Gas spiraling inward loses gravitational energy. Part of that energy becomes heat and radiation. The inner disk can shine in ultraviolet light, while hot plasma near the black hole produces X-rays. This radiation does not pass harmlessly through the galaxy. It strikes atoms, ions, electrons, molecules, and dust grains. Photons transfer momentum. Gas is heated. Dust absorbs shorter wavelength light and re-radiates it in the infrared. If the radiation field is intense enough, material begins flowing away from the center. These flows are called radiative winds. They can move at thousands or even tens of thousands of kilometers per second. Some emerge from the accretion disk itself. Others form when radiation pushes on gas and dust farther from the black hole. The central engine can also produce relativistic jets. Jets are narrow beams of plasma launched from regions close to the black hole. They are shaped and accelerated by powerful magnetic fields associated with the accretion flow, and, in some cases, the spin of the black hole. The material inside a jet can travel close to the speed of light. A jet may pierce through the galaxy and continue far into intergalactic space. In large systems, jets create enormous cavities in the surrounding hot gas. Those cavities reveal where energy has been deposited, even when the black hole itself cannot be seen directly. The displaced gas records its activity. Radiative winds and jets do not simply remove material. They collide with it. A fast outflow striking slower gas creates a shock wave. The situation resembles a supersonic aircraft producing a shock in Earth's atmosphere. But the galactic version can extend across hundreds or thousands of light years. Gas crossing the shock is compressed and heated. Its temperature may rise to millions of degrees. This is shock heating. Hot gas has greater pressure and resists gravitational collapse. It may expand outward, carry energy into the galaxy's halo, or remain suspended for long periods before cooling. The effect depends on how the outflow transfers energy and momentum. In a momentum-driven outflow, radiation or a fast wind pushes directly against surrounding material. Photons strike gas and dust. The material gains outward momentum. Dense clouds may be accelerated away from the nucleus. The process is strongest where radiation couples efficiently to matter, especially when dust is present. An energy-driven outflow develops differently. A fast nuclear wind collides with the surrounding medium and produces extremely hot shocked gas. If that hot gas cannot cool quickly, it expands like a pressurized bubble. The bubble drives a larger shell outward. Energy injected near the black hole can then influence gas much farther away. A relatively small central wind becomes a galaxy-scale outflow. The difference is important. Momentum-driven flows are governed mainly by the direct push delivered to the gas. Energy-driven flows preserve more of the original thermal energy and can produce a larger mechanical effect. Real galaxies may contain both processes at different distances and different times. The consequences can be destructive for star formation. Stars form when cold gas gathers into dense clouds. Gravity must overcome pressure, turbulence, magnetic support, and other forces resisting collapse. A GN feedback can disrupt that balance. Radiation heats the gas. Jets stir it. Shock waves increase turbulence. Outflows remove dense material from the central region. If gas is pushed beyond the galaxy's gravitational potential, it may escape into the circumgalactic or intergalactic medium. The galaxy then loses part of its future fuel supply. This is negative feedback. The word negative does not mean the process is bad. It means the feedback reduces or suppresses star formation. Even gas that fails to escape can remain unavailable for long periods. It may rise into the galactic halo, cool and fall back later in a galactic fountain. The black hole has not permanently removed it, but it has delayed the next generation of stars. In massive galaxies and galaxy clusters, a GN feedback may prevent hot halo gas from cooling efficiently. Without that heating, theoretical models often produce too many stars in galaxies that are too massive. Feedback helps explain why some large galaxies eventually become quiet. Their central regions may contain abundant matter, yet little cold gas remains available to form new stars. But black hole feedback is not always destructive. A shock wave can heat diffuse gas while compressing denser clouds. Compression raises the gas density. Higher density strengthens self-gravity. If the cloud cools quickly enough, the shock can push it closer to collapse. This is positive feedback. The outflow does not stop star formation. It triggers it. A useful concept here is Jeans stability. A gas cloud remains stable when internal pressure, turbulence, and temperature are strong enough to resist gravitational contraction. If the cloud becomes denser or cooler, the balance shifts. Its Jeans stability decreases. Gravity gains the advantage. The cloud fragments and individual dense regions begin collapsing toward new stars. An AGN-driven shock can create those conditions in selected locations. Star formation may then appear along the edges of an outflow, inside a compressed shell, or where a radio jet collides with a molecular cloud. The same active nucleus can therefore suppress star formation in one region and stimulate it in another. Scale matters. Timing matters. Gas density matters. A short burst of activity may compress clouds without removing them. A prolonged, powerful outflow may evacuate the entire central reservoir. This complexity is essential when studying the early universe. Young galaxies contained large amounts of gas. They were compact. Their gravitational potentials were still developing. Their black holes could grow rapidly while intense star formation occurred nearby. In those environments, feedback may have operated differently from the calmer systems seen today. A small early galaxy has weaker gravity than a mature giant galaxy. Gas may be easier to expel, but the same galaxy may also receive continuous fresh material from cosmic filaments. An outflow can remove gas from one direction, while new gas arrives from another. The system becomes a cycle. Inflow feeds the black hole. The black hole launches an outflow. The outflow changes star formation. Gravity and cosmic accretion later rebuild the fuel supply. The cycle repeats. This is why black holes and galaxies are described as co-evolving. The galaxy controls how much gas reaches the nucleus. The black hole controls what happens to part of that gas afterward. Neither develops in complete isolation. The little red dots offer a view into a hidden phase of this relationship. Their red colors and broad spectral features show that obscured black hole growth was common during a specific period of early cosmic history. The central engines were often buried inside dense gas. That gas did more than hide them. It absorbed their radiation, converted it into different wavelengths, and determined how much energy could escape into the host galaxy. QS01 revealed the gravitational extreme. Its 50 million solar mass black hole accounts for at least 2/3 of the mass of its compact system. The host is chemically primitive. The central object already dominates. QS01 shows that, in at least one case, the black hole reached an advanced stage before the surrounding stellar galaxy became massive and chemically mature. Glimpse 17,775 revealed the radiative environment. Its spectrum contained more than 40 features, including hydrogen, helium, oxygen, sulfur, and a forest of iron lines. Electron scattering showed that photons were passing repeatedly through dense ionized gas. The cocoon was absorbing, scattering, and re-emitting energy from the central source. Together, these objects changed the original story. Webb did not simply find galaxies that were too massive. It began separating three sources of light that had previously been blended together. Stars produce a stellar continuum and absorption features. Ionized gas produces strong emission lines. Accreting black holes generate powerful continua that can be absorbed and reprocessed by surrounding material. When all three are mixed into a few infrared measurements, a small active system can look like an enormous mature galaxy. Spectroscopy breaks that illusion. It reduces some stellar mass estimates. It identifies hidden black holes. It maps the gas through which their radiation travels. And it reveals how the central engine may be changing the galaxy around it. The early universe may not have built every galaxy by following one fixed sequence. In some systems, stars may have formed first and later fed a central black hole. In others, an early black hole may have become dominant while the stellar component was still small. Most likely, the two grew through repeated cycles of inflow, star formation, accretion, and feedback. That is the deeper lesson of the little red dots. The black hole is not an object added to a finished galaxy. It is one of the engines participating in the galaxy's construction, but the ages assigned to QSO 1 MOM-Z 14, and every distant galaxy depend on one fundamental number. That number is the rate at which the universe is expanding, and it still refuses to settle on a single value. One method gives a result near 67. Another gives a result above 73. A third lands somewhere between them. These cannot simply be called the same answer. The number under dispute is the Hubble constant. It describes how quickly cosmic expansion increases with distance in the present-day universe. Its units are kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. If the Hubble constant is close to 70, then for every additional megaparsec of distance, the recession velocity associated with cosmic expansion increases by roughly 70 kilometers per second. That does not mean every nearby galaxy follows the relationship perfectly. Galaxies also have peculiar velocities caused by local gravity. They orbit inside groups. They fall toward clusters. They move around voids and dense filaments. For nearby objects, those local motions can represent a large fraction of the measured velocity. Astronomers therefore need galaxies far enough away for cosmic expansion to dominate, but close enough for their distances to be measured accurately. The challenge is that distance cannot be read directly from an image. A faint galaxy may be nearby and intrinsically dim, or it may be extremely luminous and very far away. To separate those possibilities, astronomers construct the cosmic distance ladder. Each rung calibrates the next. The first rung relies on geometry. As Earth moves around the Sun, a nearby star appears to shift slightly against the more distant background. The effect is called parallax. A star observed from opposite sides of Earth's orbit is viewed from two positions separated by roughly 300 million kilometers. That baseline creates a tiny apparent angle. The closer the star, the larger the shift. The farther the star, the smaller it becomes. Parallax provides a distance without requiring assumptions about how a star produces light. It is geometric, but the angles become extremely small beyond the Milky Way. Parallax cannot directly measure the distances of galaxies hundreds of millions of light-years away. The next rung requires objects whose luminosities can be inferred from their behavior. Cepheid variable stars provide one of the most important examples. A cepheid expands and contracts in a regular cycle. Its outer layers pulsate. Its temperature and brightness change in a predictable rhythm. The period of that pulsation is connected to the star's intrinsic luminosity. Longer period cepheids are generally more luminous. This relationship is known as the Leavitt law, named after Henrietta Swan Leavitt, whose work revealed the pattern in the early 20th century. Once the pulsation period is measured, astronomers can estimate how much light the cepheid truly emits. They then compare that intrinsic luminosity with the observed brightness. The difference gives the distance. Cepheids can be observed in nearby galaxies containing Type 1a supernovae. Those supernovae form the next major rung. A Type 1a supernova occurs when a white dwarf undergoes a thermonuclear disruption. The precise evolutionary path can vary, but the explosions share useful relationships between their brightness and the way their light curves rise and fade. They are not perfectly identical candles. They are standardizable candles. After corrections for light curve shape, color, and other properties, Type 1a supernovae can be compared across enormous distances. Cepheids calibrate the supernovae in nearby host galaxies. The calibrated supernovae then carry the distance scale much farther into the expanding universe. Every rung introduces possible systematic uncertainty. A parallax zero point may contain a small offset. Cepheid luminosity can depend on chemical composition. Dust absorbs and reddens their light. Photometric calibration can differ between instruments. The population of stars surrounding a cepheid can contaminate its measured brightness. That last problem is known as crowding. A cepheid in another galaxy is not observed against an empty background. It may sit inside a dense field, containing dozens or hundreds of unresolved stars. If their light blends into the same apparent point, the cepheid looks brighter than it truly is. A star that appears too bright will be inferred to be too close. That error then moves upward through the distance ladder. The supernova calibrated by that Cepheid receives the wrong luminosity. The galaxies measured through those supernovae receive the wrong distances. The final Hubble constant shifts. Webb was expected to provide an important test. Its large mirror, stable position, infrared sensitivity, and high angular resolution allow it to separate stars that Hubble may partially blend together. Infrared observations also reduce the impact of dust. When Webb reobserved Cepheids, previously measured by Hubble, it confirmed that crowding existed. But the corrections did not automatically erase the high local value of the Hubble constant. That strengthened confidence in the Cepheid measurements. It did not remove every possible systematic uncertainty. Cepheid metallicity still matters. Calibration anchors still matter. Supernova population effects still matter. Different teams can make different choices about sample selection, extinction corrections, and statistical treatment. This is why independent distance indicators are essential. One alternative is the tip of the red giant branch, or TRGB. A low-mass star spends much of its life fusing hydrogen. Later, it expands into a red giant, while its inert helium core grows denser. Eventually, the core reaches the conditions required for helium ignition. Just before that transition, red giants reach a characteristic maximum luminosity in certain wavelength bands. In a color magnitude diagram, the stellar population appears to end at a sharp boundary. That boundary is the tip of the red giant branch. Because TRGB stars can be found in the outer halos of galaxies, they are often observed in less crowded and less dusty environments than Cepheids. They provide an independent route to calibrating Type 1a supernovae. Another method uses carbon-rich stars in the J region of near-infrared color space. These objects are often called J-region asymptotic giant branch stars, or JAGB stars. During a late stage of stellar evolution, some stars dredge carbon from their interiors into their atmospheres. A selected group has a relatively stable near-infrared luminosity. That makes them potential standard candles. Their brightness is measured in a wavelength range where dust extinction is lower, offering another independent check. The different methods do not yet produce one perfectly unified number. The SH0ES collaboration, using Cepheid-calibrated Type 1a supernovae, reported a value of about 73.17 kilometers per second per megaparsec, with an uncertainty of approximately 0.86. The Chicago Carnegie program, led by Wendy Friedman, using the tip of the red giant branch with Webb and Hubble data, obtained a value near 70.4 with a total uncertainty of roughly 1.9. That result lies between the high Cepheid value and the lower value inferred from the early universe. Then there is the Atacama Cosmology Telescope. ACT does not build its primary measurement from nearby stars and supernovae. It studies the cosmic microwave background and interprets that ancient radiation within a cosmological model, using ACT and Planck data within the standard lambda cold dark matter framework. The inferred Hubble constant is about 67.62 with an uncertainty of 0.50. When CMB lensing and baryon acoustic oscillation measurements are added, the value becomes about 68.22 with an uncertainty of 0.36. These measurements are related, but they are not identical experiments. The local distance ladder attempts to measure the recent expansion rate through calibrated astronomical objects. The CMB method infers the present expansion rate from conditions in the early universe, assuming a model describing everything that happened between then and now. If the model is incomplete, the inferred value could shift even when the CMB data are correct. If an unknown systematic affects the local distance ladder, the directly measured value could shift even if the cosmological model is correct. The intermediate result, near 70, prevents the debate from being reduced to two simple camps, Cepheids, TRGB stars, JAGB stars, Messier galaxies, gravitational lenses, supernovae, and gravitational wave standard sirens test different parts of the problem. Some share calibration steps, others do not. Each has different strengths and different vulnerabilities. The disagreement is therefore not just about selecting 67 or 73. It is about determining which measurements are independent, which assumptions they share, and whether one physical model can explain all of them at the same time. The distance ladder begins nearby and builds outward. ACT takes the opposite route. It begins with light released before the first star existed, before galaxies, before black holes, and before the first starlight. The universe was a hot plasma vibrating with sound waves. Those waves left an imprint that still exists today. The early universe was filled with photons, electrons, atomic nuclei, dark matter, and other particles. Temperatures were too high for electrons to remain permanently attached to protons. Any neutral hydrogen atom that formed was quickly broken apart by energetic radiation. Ordinary matter therefore existed as an ionized plasma. Photons could not travel freely through it. They repeatedly scattered from charged particles, especially free electrons. The photons and ordinary matter were tightly coupled. Astronomers call this the photon-baryon plasma. Baryons include protons and neutrons, the particles making up most ordinary atomic matter. Dark matter behaved differently. It did not interact strongly with light. It began gathering into gravitational concentrations, while ordinary matter remained coupled to radiation. Those dark matter structures created gravitational wells. The photon-baryon plasma tried to fall into them. As matter accumulated, the region became denser. Gravity pulled inward, but compression increased the pressure of the trapped radiation. That pressure pushed outward. The competition produced oscillations. Matter fell into a gravitational well. Radiation pressure resisted the compression. The plasma expanded. Gravity pulled it back again. These cycles created pressure waves moving through the early universe. They are known as acoustic oscillations. They were not sound waves traveling through air. There was no air. They were density waves traveling through a hot plasma. Still, the underlying principle was familiar. Compression and pressure created a propagating disturbance. Different regions began oscillating at different times and scales. Some reached maximum compression, others reached maximum expansion. The pattern depended on the amount of ordinary matter, dark matter, radiation, and the geometry of space. Then the universe cooled. About 380,000 years after the Big Bang, the temperature fell to roughly 3,000 Kelvin. Electrons could remain bound to protons. Neutral hydrogen formed in large quantities. This transition is called recombination, even though it was the first stable combination of many of those particles. As free electrons disappeared, photons stopped scattering so frequently. The universe became transparent. Radiation that had been trapped inside the plasma began traveling across space. That ancient radiation is the cosmic microwave background, or CMB. At the time of release, it glowed at visible and infrared wavelengths associated with a temperature of several thousand Kelvin. Cosmic expansion stretched those photons by more than a factor of 1,000. Today, the radiation has a temperature of approximately 2.7 Kelvin and appears in the microwave range. The CMB reaches Earth from every direction. It is remarkably uniform, but it is not perfectly smooth. Its temperature varies by only a few tens of millionths of a degree across the sky. Those tiny variations are among the most informative measurements in all of cosmology. They record differences in density, velocity, and gravitational potential at the time photons last scattered. The acoustic oscillations appear in the CMB as a series of peaks. Astronomers do not see the peaks as mountains in a photograph. They appear when temperature variations are analyzed according to angular scale. Some patterns cover large areas of the sky. Others are much smaller. The strength of the fluctuations at each scale produces a power spectrum. The first acoustic peak is closely related to the apparent angular size of the sound horizon at recombination. The sound horizon is the maximum distance an acoustic wave could have traveled through the plasma before the photons were released. It provides a physical scale from the early universe. If that known scale appears at a particular angle on the sky, the geometry and expansion history between recombination and the present can be constrained. The relative heights of the peaks provide additional information. Ordinary matter adds inertia to the photon baryon fluid. A higher baryon density changes the balance between compressions and rarefactions, affecting alternating peaks in different ways. Dark matter deepens gravitational wells without adding photon pressure. Its abundance changes the growth and timing of the oscillations. The peak positions and overall pattern also constrain the curvature of space. A curved universe would alter how the sound horizon appears when projected across the sky. The CMB therefore encodes the baryon density, dark matter density, spatial geometry, primordial fluctuations, and several other cosmological quantities. But it does not measure the present Hubble constant in the same direct manner as the distance ladder. The value is inferred. Astronomers fit a cosmological model to the CMB pattern. The model evolves the early universe forward in time and determines which present-day expansion rate is consistent with the observed peaks. In the standard lambda cold dark matter model, that process produces a value near 67 to 68 kilometers per second per megaparsec. The result depends on the model connecting recombination to the present. This is where the Atacama Cosmology Telescope becomes important. ACT was built in the high Atacama Desert, where dry air reduces atmospheric absorption of microwave radiation. Its final major data set, known as Data Release 6, used observations gathered from 2017 until the telescope completed its survey in 2022. ACT measured both the temperature pattern of the CMB and its polarization. Polarization describes the preferred orientation of the electromagnetic waves when CMB photons last scattered from electrons. Local differences in the radiation field produced specific polarization patterns. One of these is called E-mode polarization. E-modes form a pattern with no handed twisting direction. They provide information that overlaps with, but is not identical to, the temperature measurements, foreground emission, calibration, and instrumental effects influence temperature and polarization differently. Agreement between them strengthens confidence that the inferred cosmological parameters are not being produced by one hidden problem in the data. ACT's E-mode measurements are especially significant for the Hubble tension. Within the standard lambda cold dark matter framework, ACT's polarization data do not fit a model with a Hubble constant of 73. The disagreement exceeds 4 standard deviations. A standard deviation, often called sigma, describes how far a result lies from the expectation once measurement uncertainty is considered. A discrepancy above 4 sigma is difficult to dismiss as ordinary random noise, but the meaning must be stated carefully. A CT does not prove that the SH0ES measurement is wrong. The ACT result asks a different question. It asks whether a lambda cold dark matter universe with a present Hubble constant of 73 can reproduce the observed small-scale E-mode polarization pattern. According to the ACT analysis, it cannot. Such a model can adjust other parameters to match some CMB features. For example, it can alter the matter density to preserve the angular positions of the acoustic peaks. But those adjustments change the peak heights. The model then overpredicts the E-mode power measured by ACT at smaller angular scales. The pieces no longer fit together. This creates 2 broad possibilities. An unidentified systematic effect may remain in 1 or more measurements, or the model connecting the early and late universe may be incomplete. New physics could alter the sound horizon before recombination. It could change the expansion history after recombination. It could involve additional particles, fields, interactions, or behavior in the dark sector, but proposed extensions must do more than raise the inferred Hubble constant. They must preserve the successful fit to the entire CMB spectrum: nucleosynthesis, galaxy clustering, gravitational lensing, and other observations. That is an extremely restrictive test. The acoustic waves did not disappear when the universe became transparent. At recombination, photons escaped from the plasma, but ordinary matter retained the density pattern. Regions reached by the sound waves contained slightly more matter than regions just inside or outside that scale. Over billions of years, gravity amplified the structure. Galaxies formed preferentially in the denser regions. The original acoustic scale therefore survives as a small statistical excess in the separation between galaxies. This fossil is called baryon acoustic oscillation, or BAO. The scale is enormous. In the present-day car-moving description of the universe, it is roughly 147 megaparsecs, or close to 480 million light-years. No visible shell surrounds each galaxy. The signal emerges only after the positions of millions of galaxies and quasars are analyzed statistically. A galaxy has a slightly increased probability of having another galaxy located near the BAO scale. That turns the sound horizon into a standard ruler. Its apparent size across the sky measures cosmic distance. Its extent along the line of sight measures how redshift changes with distance. By observing BAO at different epochs, astronomers reconstruct the history of cosmic expansion. The CMB reveals the ruler when it was established. Galaxy surveys reveal how that ruler appears after billions of years of expansion. This is why ACT and BAO form such a powerful combination. ACT constrains the early universe physics and the original sound horizon. BAO carries that scale through later cosmic history. Together, they infer a Hubble constant near 68 with extremely small formal uncertainty. That acoustic ruler does more than measure the universe today. DESI has placed it at multiple moments in cosmic history and found that the expansion may not be as simple as a constant force. DESI used nearly 15 million galaxies and quasars to trace roughly 11 billion years of cosmic expansion. The data do not declare that dark energy is changing, but when DESI is combined with other major observations, the evidence begins leaning in that direction. DESI stands for the Dark Energy Spectroscopic Instrument. It is mounted on the 4-meter Nicholas U. Mail telescope at Kitt Peak National Observatory in Arizona. The telescope collects the light. DESI performs the extraordinary task of separating and measuring it. At the instrument's focal plane are 5,000 robotic fiber positioners. Each one can direct an optical fiber toward a selected object in the sky. During a single exposure, DESI can collect light from as many as 5,000 galaxies or quasars. After the exposure, the robotic positioners move. A new set of targets is selected. The process repeats throughout the night. The light travels through the fibers into spectrographs, where it is separated by wavelength. Emission lines, absorption lines, and spectral breaks reveal each object's redshift. A two-dimensional image shows where a galaxy appears on the sky. Redshift provides the third dimension. With millions of measurements, DESI turns points of light into a three-dimensional map of the cosmic web. The map contains galaxy clusters, long filaments, underdense voids, dense knots where structures intersect, and quasars so distant that their light passed through intergalactic hydrogen for billions of years before reaching Earth. DESI does not measure dark energy directly. No detector records a dark energy particle. No image shows dark energy as a visible substance. Instead, DESI measures how the universe expanded and how matter became distributed. Dark energy is inferred from those effects. One of DESI's most important tools is baryon acoustic oscillation. The BAO scale began as a pressure wave inside the photon baryon plasma before recombination. When photons separated from ordinary matter, the wave stopped propagating in the same way, leaving behind a preferred scale in the matter distribution. That scale remains statistically visible in the separation between galaxies. It acts as a standard ruler. The ruler is not printed across the sky. It appears when enormous numbers of galaxies are compared. For any one galaxy, there is a slightly increased probability of finding another galaxy near the BAO distance. The signal is weak. The sample must be huge. With enough galaxies, the pattern emerges. DESI measures the ruler in two directions. Across the sky, its apparent angular size provides information about cosmic distance. Along the line of sight, its redshift extent reveals how rapidly distance changes with redshift. Together, these measurements reconstruct expansion at different epochs. A ruler observed nearby records the recent universe. A ruler observed at high redshift records an earlier stage. By placing the same physical scale at many points across cosmic history, DESI tracks how the expansion rate changed over billions of years. That history is sensitive to dark energy. Under the standard lambda cold dark matter model, dark energy is represented by the Greek letter lambda. Lambda acts as a cosmological constant. Its energy density remains constant as space expands. Matter behaves differently. As the universe grows, ordinary matter and dark matter become diluted. The same amount of matter occupies a larger volume. Radiation becomes diluted even faster because the number density of photons falls while their wavelengths are also stretched. A cosmological constant does not dilute in the same way. Its density stays fixed. That means its relative importance grows as matter becomes more spread out. In the early universe, matter dominated the expansion history. Several billion years ago, dark energy became dynamically important. Cosmic expansion began accelerating. Physicists describe the behavior of dark energy using an equation of state parameter. This parameter compares pressure with energy density. For a true cosmological constant, its value is exactly -1. That value corresponds to a component with negative pressure powerful enough to drive accelerated expansion while maintaining constant energy density. If the value differs from -1, dark energy may behave differently. If it also changes with cosmic time, then dark energy is dynamic rather than constant. The measurement is difficult because several cosmological parameters can imitate one another's effects. Changing the matter density alters expansion. Changing spatial geometry alters observed distances. Changing the calibration of the sound horizon alters the BAO ruler. Changing supernova luminosity calibration alters inferred distance. No single dataset can freely vary all those quantities without creating degeneracies. That is why DESI is combined with other observations. The cosmic microwave background anchors conditions in the early universe. It constrains the sound horizon, baryon density, dark matter density, and primordial fluctuation pattern, type 1, in supernovae provide a different kind of distance information. After their light curves and colors are standardized, their observed brightness reveals relative distance across cosmic time. BAO measures a standard ruler. Supernovae measure standardizable candles. The two methods respond differently to calibration errors and cosmological parameters. Weak gravitational lensing adds another perspective. Matter bends the light of background galaxies. Large-scale structure produces tiny, coherent distortions in their observed shapes. Any one galaxy already has its own unknown shape. So, the lensing signal cannot be trusted from a single object, but across millions of galaxies, the random intrinsic orientations average out. A small statistical alignment remains. That pattern reveals how matter is distributed and how structures grew. Dark energy affects both expansion and structure growth. Faster expansion can slow the assembly of matter by increasing the distance between unbound regions. Weak lensing therefore tests whether the matter distribution evolved consistently with the expansion history inferred from BAO and supernovae. When DESI's first 3 years of measurements are considered alone, they remain consistent with lambda cold dark matter. That point is essential. DESI by itself has not rejected a cosmological constant. The tension becomes stronger when DESI is combined with CMB measurements, supernova datasets, and weak lensing information, depending on which combination and which supernova catalog are used. The preference for evolving dark energy ranges from about 2.8 to 4.2 sigma. That is interesting. It is not a discovery. In physics, 5 sigma is commonly used as the threshold for announcing a new phenomenon. The standard is intentionally demanding. A result near 3 sigma can look persuasive and later disappear. More data may reveal a statistical fluctuation. A calibration problem may emerge. An underestimated systematic uncertainty may widen the error range. Even a 4 sigma signal requires caution when it arises from combining complex datasets. Each survey has selection effects. Each supernova catalog has calibration decisions. Weak lensing measurements require careful correction for telescope optics, atmospheric effects, galaxy shapes, and redshift estimates. CMB analyses require foreground removal. BAO analyses depend on survey geometry and statistical reconstruction. The fact that several independent lines of evidence lean in a similar direction makes the result more compelling. It does not make the result final. There is also no model-independent measurement showing that dark energy has weakened by one fixed percentage. Statements about a 10% change depend on how dark energy is parameterized and which datasets are included. The observations constrain distances and structure. Researchers then test models describing how a dark component would need to behave to reproduce those measurements. Different parameterizations can translate the same observations into different descriptions of change. The safest conclusion is narrower. A constant dark energy component still fits DESI alone, but when the best available measurements are analyzed together, a model in which dark energy evolves can fit the combined data better than the simplest constant model. This is a data tension. Each instrument may be working correctly. Each dataset may appear reasonable on its own. Yet one simple cosmological model has difficulty occupying the preferred region of all of them simultaneously. The situation resembles the Hubble tension. The problem is not necessarily that one measurement is obviously wrong. The problem is that several high-precision measurements resist a single shared explanation. More DESI data may strengthen the pattern. They may also move it back toward the cosmological constant. Future supernova samples, improved weak lensing surveys, and independent BAO measurements will test whether the preference survives. Until then, dark energy remains a name for an observed effect, not a known physical substance. Its influence is measured. Its nature is not. If dark energy is not constant, the future of the universe changes. But what does the current evidence actually allow, and what still lies beyond it? Humanity has measured light released only 280 million years after the Big Bang. Yet it still cannot say with certainty what will happen in the most distant future. The answer depends on dark energy. It also depends on whether the standard cosmological model continues to describe the universe across timescales vastly longer than anything directly observed. Under the baseline lambda cold dark matter model, dark energy is a cosmological constant. Its density does not fade as space expands. Matter becomes more diluted. Radiation loses energy as its wavelengths stretch. Dark energy eventually dominates the large-scale dynamics more completely. Expansion continues, and it accelerates. This does not mean every object is torn apart. Gravity holds the solar system together. It holds stars inside galaxies. It binds many galaxies into groups and clusters. Cosmic expansion acts most clearly across distances where local gravity cannot keep structures connected. The local group is gravitationally bound. Distant galaxies outside bound structures are not. As expansion continues, those galaxies reseed more rapidly. Their light becomes increasingly redshifted. Photons emitted toward the Milky Way lose energy during their journey. The galaxies grow fainter. Eventually, many cross a cosmological event horizon. This horizon is not a physical wall. It marks a limit created by accelerating expansion. Beyond it, light emitted at sufficiently late times can never reach the observer. No matter how long the journey continues, the galaxy still exists. Its future signals simply become causally inaccessible. Over immense time, the observable universe around any surviving civilization would appear emptier. The evidence of the wider cosmic web would fade. The cosmic microwave background would be stretched to wavelengths so long and energies so low that it would become extraordinarily difficult to detect. Future astronomers might live inside a bound remnant galaxy with little observational evidence that other galaxies had ever filled the universe. The stars would also change. Cosmic star formation has already passed its peak. The universe formed stars most rapidly billions of years ago. The rate has declined because galaxies have consumed, heated, or expelled much of their cold gas. New stars will continue forming for a very long time. But the available fuel will gradually decrease. Massive blue stars will disappear first. They live only millions of years. Sun-like stars last billions. Low-mass red dwarfs can burn for trillions of years because they consume hydrogen slowly and efficiently. Eventually, even those long-lived stars will exhaust their fuel. If no new gas reservoirs remain capable of collapse, the era of ordinary star formation will end. The universe will enter a period dominated by stellar remnants, white dwarfs, neutron stars, brown dwarfs, cold planets, and black holes. Gravitational encounters may eject objects from galaxies. Some remnants may collide. Rare processes may continue releasing energy. But the universe will no longer contain the widespread starlight familiar today. On still longer model-dependent timescales, black holes become important. Quantum field theory predicts that black holes are not perfectly eternal. Through Hawking radiation, they can lose mass extremely slowly. For a black hole with the mass of the Sun, the evaporation time is unimaginably longer than the current age of the universe. Supermassive black holes require even longer, depending on mass. Their lifetimes extend across numbers of years, containing dozens or even around 100 digits. Nothing in human experience provides an intuitive comparison. When the final black holes evaporate, the remaining universe would contain extremely low-energy radiation and sparse particles separated by expanding space. The destination is often called heat death. The name does not mean everything becomes hot. It means the universe approaches thermodynamic equilibrium. Useful energy differences disappear. A heat engine requires a contrast. A hot region and a cold region, a high-pressure reservoir and a low-pressure one, concentrated fuel and an environment into which waste energy can be released. As entropy approaches its maximum allowed state, those contrasts become harder to find. Energy still exists, but less of it remains available to perform organized work. The universe becomes colder, darker, more dilute, and less capable of producing change. This is the big freeze or heat death future. Under the current baseline model, it is the leading long-term outcome. It is not an observed ending. No telescope has watched it happen. It is a projection obtained by extending the measured properties of the universe and the cosmological constant into the future. If dark energy behaves differently, the projection changes. One alternative is the Big Rip. This outcome requires a form of dark energy whose density increases as the universe expands. Such behavior is sometimes called phantom energy. In that scenario, accelerated expansion does not merely continue at a roughly stable dark energy density. The repulsive effect becomes progressively stronger. At first, unbound galaxy clusters separate. Later, the expansion could overpower the gravity holding individual galaxies together. If the effect continued without limit, it could eventually exceed the forces binding solar systems. Planets, molecules, and even atoms. The sequence ends in a finite time with structures torn apart at progressively smaller scales. But the Big Rip is conditional. It requires dark energy to remain in the necessary phantom regime and to continue behaving that way into the distant future. The DESI results do not establish that condition. A temporary preference in a fitted parameter is not evidence that the same behavior will persist forever. Current data do not justify presenting the Big Rip as an equally supported rival to heat death. The Big Crunch requires a different reversal. Expansion must slow, stop, and become contraction. Matter would then move closer together. The cosmic microwave background would heat rather than cool. Galaxies would approach and merge. Density and temperature would rise as the universe collapsed. In older cosmological discussions, the outcome was often connected mainly to whether the universe contained enough matter for gravity to reverse expansion. Dark energy changes that reasoning. A spatially flat universe can still continue expanding forever. A future collapse would require the effective cosmic dynamics to change substantially, possibly through dark energy decaying, becoming negative, or otherwise allowing gravity to regain control. No current observation confirms that such a reversal will occur. The universe is accelerating now. A future Big Crunch therefore requires physics beyond the simple continuation of the measured present state. The three endings are not three equally likely doors. Heat death follows from extending the baseline lambda cold dark matter model. The Big Rip follows only if a specific form of increasing dark energy persists. The Big Crunch follows only if the expansion dynamics change enough to reverse the present acceleration. The distinction matters because dramatic possibilities can sound more certain than the data allow. The honest ending is less theatrical. The universe has not yet provided enough information to reveal its final state. That uncertainty connects every part of the story. Webb measures the light of the first confirmed galaxies and places them inside the first few 100 million years. ALMA reads the chemistry of their gas and detects oxygen produced by early stars. NIRSpec's integral field unit maps gas motion and weighs a black hole through its gravitational influence. ACT reads the acoustic structure of the primordial plasma and infers expansion through the standard cosmological model. DESI follows the fossil ruler of those same acoustic waves across 11 billion years. No instrument tells the entire story. Each measures a different physical trace: light, chemistry, motion, polarization, galaxy clustering, gravitational distortion. The strength comes from combining them. The tension also comes from combining them. A model may fit one dataset beautifully and struggle when another is added. A galaxy may appear impossibly massive until black hole light is separated from starlight. A red source may look distant until spectroscopy reveals dust. A constant dark energy model may match DESI alone while fitting the combined data less comfortably. These are not signs that science has failed. They are signs that science is working correctly. A model is not protected because it is elegant. A measurement is not accepted because it is dramatic. Every claim remains exposed to a better spectrum, a larger sample, a different wavelength, or an independent method. Each improved measurement has the right to revise the previous story, and every time the universe forces humanity to admit that an answer is incomplete, the frontier of discovery expands again. MOM-Z14 showed a bright galaxy only 280 million years after the Big Bang. JADES-GS-Z14-0 showed oxygen when massive stars had barely enough time to live and die. QS01 showed a 50 million solar mass black hole dominating a chemically primitive system. Little red dots revealed a hidden phase in which black holes, gas, and stars produced light that earlier models had blended together. ACT showed that the early universe inference remains stubbornly close to 67 or 68. DESI showed that the simplest description of dark energy may not fit every modern dataset at once. None provides the final answer. Together, they provide something more valuable. They show exactly where the existing story becomes uncertain. The most astonishing fact is not how large the universe is. It is that, within its first few 100 million years, it had already become far more complex than humanity ever imagined.